everybody, welcome back. So in this video, I'm just going to go through question 10 on the homework assignment. So in this one, we're dealing with an amusement park ride. So you have riders on an amusement park ride, shaped like a Viking ship, hung from a large pivot, rotated back and forth like a rigid pendulum. So sometime near the middle of the ride, the ship is momentarily motionless at the top of its circular arc, and then the ship swings down under the influence of gravity. So perhaps you've seen this amusement park ride. If you've been to the fair or other amusement parks, you have like the pirate ship or the Viking ship in this case. So we start in the middle and kind of start off relatively slow here, and then we get bigger and bigger arcs. And then, at one point we get all the way up here, and then we go all the way there. And then again, it kind of starts slowing down again and then stops. So that's kind of the route of the ride there. So at one point, it's motionless up here, and then just the force of gravity moves it forward in this arc there. So assuming negligible friction, so assuming that there's oil around the different axles and different things along those lines there, so where there's not much friction to take account of. Find the speed in meters per second of the riders at the bottom of its arc, given the system's center of mass travels an arc having a radius of 13.8 meters, and the riders are near the center of mass. All right, so you have the radius is 13.8. So this is our arc here, and we're trying to figure out the speed at the bottom here. So you're starting off at rest here. So the speed is 0 here, and then we have a lot of potential energy, and that potential energy is going to get converted to kinetic energy or energy of motion there. So it says you might need some of these energy concepts from the next chapter. So you are going to be utilizing those for this section here. All right. So energy is conserved. So it's transferred from one form to another. In this case, it's being transferred from potential energy to kinetic energy. So you start off with mainly potential energy up here, and then at the bottom, we end up with mainly kinetic energy there. All right, so the potential energy is going to be your mass times your gravity times the height that you are above the ground here. All right. So in this case, the height is our radius. So the height is 13.8. All right, so you have m times g times h. And again, that's all going to be converted. So this is kind of the before. This is going to be the after. So before we just have potential energy. So again, we're stopped there, so there's no kinetic energy. And then after, that potential energy is going to be converted to kinetic energy there. And the formula for kinetic energy is 1/2 mv squared, where v is our linear velocity. All right. So here we have the mass shows up on both sides, so we can cancel out that. We're dividing both sides by the mass there. So we end up with g times h equals 1/2 v squared. So to get rid of the fraction, we can multiply by 2. So we have 2gh equals v squared, which we can then, to get v by itself, we can take the square root. So we end up with v equals the square root of 2gh. All right, where again, h is going to be my radius here. So if we take the square root of 2 times 9.8 meters per second squared times h, which is 13.8. We should end up with 16.45 meters per second. So they rounded to 16.4. You can round it there as well. All right. So that is the linear acceleration, or linear velocity. So that's my answer to part A. And then part B asks us to find the centripetal acceleration at the bottom of the arc. So again, centripetal acceleration is the acceleration of the force that's keeping the ship, in this case, attached there. So in this case, it's going to be kind of the centripetal acceleration is going to be provided by the tension force of the rods here. All right. So yeah, so the centripetal acceleration, if we look at our handy dandy sheet here, so yeah, so the centripetal acceleration is going to be v squared over r. So yeah, so once we know the v, and we know the r is given in the question, and the v is what we just found out. So yeah, so in this case, we're going to have 16.45 squared over r, which is 13.8. And I'll go ahead and use the rounding that they provided. So I'll use 16.4 squared, I guess, divided by 13.8. And that gets me 19.5 meters per second squared. All right. So yeah, so again, they get 19.6. Again, it's fairly comparable. Let's see what would happen if I use the 16.45. All right, 16.4 squared divided by 13.8. Yeah, I ended up with 19.6. So yeah, so I don't know. In my opinion, their lack of consistency makes this. So yeah, so again, it should count both these answers correct. There. All right. So yeah, so in this case, looking at the diagram. So yeah, so looking at the normal force, so the normal force is going to be the centripetal force plus the weight of the rider. So yeah, so the centripetal force is the force holding the boat in, but you also have the weight of the boat also needs to be counteracted by that normal force as well. So yeah, so in this case, the normal force is going to be longer than the weight, and again, it's going to be pointing towards the center of the ride. So yeah, so it's going to be that first option there. So then to actually find the normal force, so the force exerted by the ride on a 79 kilogram rider. So yeah, so we have the centripetal force plus the weight of the rider. So yeah, so that part kind of confused me. I had to do a little bit of research with regards to that, but yeah. So yeah, so your normal force is again going to be your centripetal force plus the weight of the rider. So yeah, so our normal force again is providing the force to keep everything in the ship, and then also it has to counteract again the weight of the rider as well. All right, so yeah, so the centripetal force is going to be m times v squared over r, or m times your centripetal acceleration. So you have 79, I think it's just 79. Yeah, so you have 79 kilograms here times my centripetal acceleration, which is 19.6 according to them, plus the weight of the rider. So you have 79 times the acceleration due to gravity, so 79 times 9.8 there. So yeah, so we're going to take 79 times 19.6 plus 79 times 9.8. We should end up with something around, yeah, I get 2322.6. This is in newtons. So yeah, so they round it again to 2320 there. All right, and that's D actually. All right. So yeah, so then we're asked to compare it to their weights. All right, so in this case, we just need to take the normal force here and divide it by their weight. So yeah, so you have 2320 divided by 79 times 9.8. So yeah, so we have the normal force divided by the force of gravity, so their weight. So 2320 divided by 79 times 9.8. End up with 2.99, which, yeah, they approximate to 3. So, yeah, so we have 3 times their weight there. Yeah, which is why you do kind of feel heavier on these rides as it goes down there. So yeah, so hopefully you found that helpful. Yeah, have a good day, and I'll talk to y'all later. Bye now.